Before I go on to part two with the exponential growth, I want to talk about one more thing, which involves what your exponents or what your growth functions look like. So we're going to use the red line as kind of our go-to comparison line. And if I graph y equals 2 to the x power, that's my red line. Okay? What you need to know here is that your y-intercept on this is 1, because if you were to have an a value, that equation would be y equals 1 times 2 to the x power. Now, why can't you have a 0 there? Because a 0 would be, that's what your y-intercept is. And if I have a y-intercept of 0, then it's touched my x-axis, which an exponential growth equation never touches the x-axis. So the lowest number that you're going to have there is 1 as a whole number. Now, let's take a look at the blue line, which is y equals 3 times 2 to the x power. You can see here my y-intercept is 3, therefore my a value is 3. Now, because this is a much steeper slope, a much steeper equation than y equals 2x, we know that this blue one is what we call a vertical stretch. It's a vertical stretch of y equals 1 times 2 to the x. Now notice the green line down here. It is still a growth equation, but it grows downwards. Now the only difference here is, what is your y-intercept? Your y-intercept is -3. So what this looks like is it starts from left to right, but it goes down really quick. Now, this is what we call a vertical stretch also, but it is a vertical stretch with a reflection on the x-axis. So I will type that here for you. It is a vertical stretch with a reflection in the x-axis because it reflects over the x-axis. So you have a vertical stretch, which is still on the same side of the x-axis as that red equation, but then if it's on the opposite side, if your a value is negative, then it's a vertical stretch with a reflection. So two key vocabulary terms there, vertical stretch and vertical stretch with a reflection. Now let's go ahead and move on to that exponential growth formula where we can see potentially money growing at a pretty fast rate. So whenever we use the exponential growth formula, it looks very similar to exponential, just the exponential growth, but this is a growth rate. All we know here is our a value is still our a value, just like in our original equation. But our b value right here, that 1 plus r, that's your b value. And then the t is represented as your x value. Now, in this equation, what we want to take a look at is what each part of the equation represents. So what you need to know here is this a value, that is your initial amount. So if you have money you're putting into the bank, what is that initial deposit that you're putting in? So it's the initial amount, the amount that you start with before any money grows. So if I have $500 and I put $500 into the bank, then my a value is 500. Now the next part is this r value. Okay, that r value is the growth rate. So r value, growth rate. I would strongly suggest adding this diagram into your notes as well. So r is the growth rate. The next part is looking at what is 1 plus r. So looking at the whole thing in parentheses, what's the 1 plus r? The 1 plus the r is the growth factor. So your growth rate is just the R, but your growth factor, your growth rate is just the R, but your growth factor is what 1 plus R equals. And then T, as you can imagine, is representing time. So how many years is your money going to grow? So let's take a look at an example with that model. Make sure again that you have that model, that entire diagram in your notes. So let's say that in 1980 a comic book was worth $55. If the value has increased at a 2.8% rate each year, what would be the value in 2018? So the first thing we know is our A. Our A value is our initial amount, so we're going to put 55 in for A. So we have 55 in the place of A. 1 stays as 1, but what's my rate? My rate is 2.8%, but don't forget to change that to decimal form. So it's decimal point 0.028. My growth factor would be the 1 plus the 0.028. And then the time. How much time has elapsed? How much time has passed from 1980 to 2018? Well, 1980 to 2018 is a total of 38 years. So our T value is 38. We're going to put 38 right up in here. And then we just follow our order of operations and we simplify the right side of the equation. So you're going to take 1.028, 1 in 28 thousandths. You're going to raise that to the power of 38 for 38 years. Once you have that answer, multiply it by the initial value of the comic book, which was 55, and you will get an answer of y is equal to, now we do have to do some estimation, so we're going to say is about equal to $157.07. So over 38 years in time, this comic book almost tripled in its value. Wouldn't that be nice if our money tripled in value as well? Let's take a look at what would happen if you were to earn 4% annually. So growth compounds over time every single year. So we're going to use that exponential growth formula again, and this time our initial amount is $5,000. So we start with $5,000. My rate is 4%, so we have 1 plus 0.04, which means my growth factor is 1.04. And how much would I have after 8 years? So I need to start off by taking 1 in 400ths, 1.04, raise it to the power of 8, and then multiply that by $5,000, and I get an answer of almost or right about $6,842.85. So at 4% interest in 8 years, you can really earn quite a bit more money than what you started with. So this is simply just making sure that you know that A is your initial amount, R is the percent, the rate, change it to a decimal, and T is your time. Then follow your order of operations and solve or just simplify the expression. Now your homework, just like lesson 7.3, is going to be a 2-part section. So day 1, I want you to work on the worksheet 7.4. I will have that for you in class, so get that from me. And then day 2, you are working on page 462. Make sure that you check your answers on the worksheet first so that anything that you need to fix for mistakes on the worksheet, you make those changes by the time you do page 462. Again, ask me if you have questions. Otherwise, good luck, and our next lesson will be exponential decay, which is what I call exponential depressing. Thank you for watching. Enjoy your night.